Hello and welcome to lecture 24 of the course Theory of Computation. In lectures 22 and 23, we have been going through the proof of the equivalence of context-free grammars and push-down automata. In 22, we saw that for given any grammar, we can construct an equivalent push-down automata. In 23, we started proving that given any push-down automata, we can we can construct a context-free grammar. So we in fact constructed the grammar in lecture 23, and there was some part of the proof that was yet to complete, which we will complete in lecture 24. Right. So the rules. So the claim was that given a push-down automaton, we can construct a context-free grammar that is equivalent to that, right? So the rules of the grammar was the following. So given a push-down automata P, right? The grammar that is constructed included variables like this A, P, Q, where we wanted the variables A, P, Q to derive all the strings that can take. So P and small q are the states of the push-down automaton, right? So we wanted APQ to derive all the strings that can take the push-down automaton from the state P to the state Q on an empty stack, right? From the state P on an empty stack to the state Q on an empty stack, right? So this is what the variables were, and the rules of the grammar were the following, right? Which we said in the previous lecture. So if P, Q, R, S are states of the PDA, so this Q is a set of states of the PDA, right? And T is a symbol in the stack alphabet of the PDA, and A, B are from sigma subscript epsilon, which means they are part of the input alphabet. They are symbols of the input alphabet, or they could be empty strings as well. So if P, Q, R, S are states, T is a symbol in the stack alphabet, and A and B are symbols in the input alphabet or empty strings, right? Then if we check if RT is part of delta PAE and Q epsilon is part of delta SBT, if these two are there, then you add the rule APQ gives A, ARS, B, right? So A is a symbol of the input alphabet, B is a symbol of the input alphabet. The A and B could either or both be empty string epsilon, and ARS is another variable, right? And the second rule was that for all the states P, Q, R, we add the rule APQ gives APR and ARQ. And the final set of rules was that for all the states P, we add APP yields epsilon, right? So these are the three set of rules that we are adding, and for each set there could be multiple such rules, right? For instance, the last rule, for each state in the PDA, we will add one such rule. And what we wanted to show was that if APQ generates X, then X can take the PDA from the state P with empty stack to the state Q with empty stack, and the converse of that. So these are in claim 2.31 and 2.30 and 2.31, right? So first let us try to prove the proof of claim 2.30. So statement is that if APQ generates X, then X can take the PDA from P with empty stack to Q with empty stack, right? So like I said in the previous lecture, if a string can take the PDA from P to Q on an empty stack, it can also take it from P to Q by retaining whatever the stack contents were, right? So this is just to recall, and the proof is by induction on the number of steps in the derivation of X, right? So the claim is that if APQ generates X, then it can do this. So how many steps does the generation of X from APQ take, right? So this is the induction, right? So before getting into the proof, I just want to say one more thing. So the proof of claim 2.30 and that of claim 2.31 may seem like long proofs, but they are actually not that difficult. So they are kind of very standard approaches, and both of them use induction, and both of them are fairly straightforward things. So don't be kind of scared by the proof or scared by the kind of terminology that is used in the proof. It's basic common sense that is applied to some setting. So once you get past the notation and understand what is going on, it should not be that difficult, right? So don't be scared by the notation. It is just basic induction, which is basic common sense. So not really much to get scared about. Okay. So coming back to 2.30's proof, it is induction on the number of steps in the derivation of x. So when I say derivation from APQ. So the base case is that APQ generates x in one step, right? So if you look at the rules, these are the three types of rules, right? APQ gives A ARS B, APQ gives this, and APQ gives epsilon. The only way that one variable generates a string comprising of entirely terminals is if we take the third in one step, right? So we want, the base case is that it generates in one step. So the only way we can get a string in one step is by taking the third rule, right? So the only possible one step derivation is the third rule, APP gives epsilon for some state P. So which means the string that is derived is empty string, right? So the requirement is that if APP generates epsilon, we want to show that epsilon can take the PDA from the state P to itself on an empty stack, right? So epsilon is the empty string, and empty string kind of trivially keeps the PDA in the same state, right, by retaining whatever the stack was. So this is true in the base case. So base case is true. Now let us move to the induction step. So suppose it is true for some k steps, right? So now we want to take the case where APQ derives the string x in k plus 1 steps, right? So let us see what is the first step of the derivation, right? So APQ is a single variable. What is the first step of the derivation? So the first step of the derivation is either a rule of this type, APQ gives A ARS B, or a rule of this type, APQ gives APR ARQ. So this gives us two cases which we will see. So let us say the first step was this, APQ gives A ARS B. So recall that eventually we want to get to x, right? So somehow we want to get to something, and finally we want to get to x, which means A ARS B is somehow derived into x, which means x begins with A and ends with B. Again, recall that A and B are either symbols of the input alphabet or it could be empty strings as well, right? But they are not like longer strings of the input alphabet, right? So this means that x is of the form A some string B, where ARS derives the middle string, right? So this means that x is of this form, AYB, where A and B are either single symbols from the input alphabet or empty strings, and Y is some string from the input alphabet, right? So where Y is in sigma star, right? And ARS must derive Y, right? And ARS will derive Y in k steps because A and B are terminals. So the rest of the derivation is merely ARS deriving Y, right? And so since one step is already over, ARS derives Y in k steps. This means that since ARS derives Y in k steps, and since by induction we may assume that Y takes the PDA from the state R, right, from the state R to the state S on an empty stack, right? But this is what we can get by induction, right? This is a statement we want to prove for k plus 1. We can assume the same for k, right? So Y takes the PDA from R to S on an empty stack, right? On an empty stack. So now we know that this is a rule, APQ gives A ARS B is a rule because that's the first step, so that must be a rule, right? But why is this a rule? This is a rule. When do we add such a rule? If these conditions are satisfied. The conditions being RT gives delta PA, RT is in delta PAE and Q epsilon is in delta SPT, right? So we know that RT is in delta PAE and Q epsilon is in delta SPT, right? So this means that the symbol A can take, so the PDA can read A, right, and go from P to the state R by pushing T into the stack, right? So there is pushing T into the stack. This is what this rule means. RT is in delta PAE. And also the PDA can go from state S to state Q, right, by reading B from the input and by popping T from the stack. That is what this rule states. So A can take the PDA, I'm explaining this, A can take the PDA from state P to state R by pushing T, and B can take the PDA from state S to state Q by popping T. And by induction, what we have already explained, Y takes the PDA from R to S by retaining the stack contents. Y takes PDA from R to S by on an empty stack, which means Y can also take the PDA from R to S by retaining the stack contents. So which means this, right? So now let's say initially the stack was empty. By reading A, right, by reading A, the PDA pushes T into the stack and then goes to the state R, right? By reading A, it goes to the state R, state P initially and then state R, and then there is a string Y. By reading Y, the PDA can go to the state S by on an empty stack or by retaining the stack contents. And finally, by reading the symbol B, it pops the stack content, the symbol T from the stack, and then it takes it from S to T. Sorry, it takes the stack from S to T, right? Which means by reading AYB, the PDA, the string AYB takes the PDA from P, the state P, to the state T on an empty stack. I'm sorry, I misspoke. I meant the state Q, not T. Right. Okay. Once again, A takes the PDA from P to R by pushing the content T. Y takes the PDA from R to S by retaining the stack content, and B takes the PDA from S to Q by popping T. So AYB takes the PDA from P to Q on an empty stack, and we know that what is AYB? AYB is nothing but X. So we know that X can take the PDA from P to Q on an empty stack, which is what we want to show. Okay. So this is the case 1 of this part of the proof. So the next part is that what if the first step of derivation was this, right? So the first step of derivation was APQ gives APR ARS, right? This means, so finally, so again, like I said before, finally some rules are applied and finally we should get X, right? But how can that happen? The only way this can happen is the variable APR generates some Y and the variable ARQ generates some, so I think there is an error again here, ARQ, not ARS. ARQ generates a Z, right? And APR generates Y and ARQ generates Z, and where X is YZ, right? So this means that X can be generated like this. So the first step is already done, right? APQ gives APR ARQ. So the remaining number of steps is K. So which means APR must generate Y in some number of steps, ARQ must generate Z in some number of steps. Both the number of steps is at most k, because together we are using only k plus 1 and 1 is already over, right. So now since both of them use at less than k steps, we can use induction to infer that Y takes the PDA from P to R on an empty stack, right, and Z takes the PDA from R to S on an empty stack, right, because we assume that for all the strings that have less than k steps of derivation, right. So this is what we said here. Suppose it is true for k steps, and now we are trying to prove something that requires k plus 1 steps, right. So by induction, Y takes P from P to R on an empty stack, and Z takes P from R to S on an empty stack. So X is just the concatenation of Y and Z, which means X takes the PDA from P to Q on an empty stack, right. So the claim is true in this case as well, because you can think of it like this. So Y and Z together form X. So Y takes it from P to R and Z takes it from R to Q, not S. Right. So the entire string YZ, which is the same as X, takes it from P to Q on an empty stack. So we have shown that whatever may be the case, whether it is the first rule applied is APQ gives AR as B, or APQ gives APR ARQ, whatever be the case, we have shown that the string that is generated will take it from P to Q on an empty stack. So this completes the proof of claim 2.30, which says that if a string is generated by APQ, that string can take the PDA from P to Q on an empty stack, or by retaining the stack content. So the next thing to be proved is claim 2.31, which is the other direction, right. Suppose there is a string X that can take the PDA from P to Q on an empty stack, then that string is generated by APQ, right. Like I said before, this is also an induction which is straightforward. So here the assumption is that the string takes the PDA from P to Q on an empty stack. So how many steps of the PDA, how many transitions of the PDA is required to generate that string? So the induction is on that number of steps, right. So induction on the number of steps required by the PDA in the PDA computation. So the simplest case is when the computation has 0 steps, the PDA doesn't do anything. So when in 0 steps, the PDA is not able to read anything, which means the string corresponding to that is, there is only one string that can be read without any number of steps, which is the empty string, right. Right. So the empty string keeps the PDA in the same state, or can keep the PDA in the same state, because that's right. Because that is the only thing that it can do, right, because we assume that the computation has 0 steps. So in 0 steps, the PDA can only process the empty string. So the empty string is empty, and let's say it was in state some state small p, and we know that APP gives empty string is a rule. So this empty string is generated by the grammar. So we assume if the computation of the PDA has 0 steps, the only string possible is empty string, and that is generated by the grammar, right. So now we have to consider the computations of a bigger number. Okay. So suppose the claim is true whenever the PDA requires some k steps for some k. Okay. Okay. So now we want to show it for k plus 1 steps, right. So now we have a string X, right, which which takes the PDA from P to Q on an empty stack using k plus 1 steps, and then we have to show that APQ generates X. So like in the other claim, we have two cases, right? The assumption is that for all the strings that take PDA from one state to another using k steps or less, the corresponding variable in the grammar generates this. Now we are considering such a string for which the PDA requires k plus 1 steps. Okay. So there are two cases which we had kind of referred to in the previous lecture. First case is the stack never becomes empty, right? So the PDA starts, it takes from empty stack to empty stack. So we know that the first step involves a push, right? And the last step, again we end at an empty stack, which means it must involve a pop, right? So if the stack never becomes empty, the symbol that was pushed in the first step must be popped only in the last step or the k plus 1 step. So assume that the symbol is T. Okay, so T is something in the tape alphabet. Right. Let the first symbol that is read from the input, right? So when pushing that symbol T, the stack must be the PDA must be reading something from the input, right? Let that symbol be A, right? And in the k plus 1 step, the symbol be B. So notice that, recall that A is part of sigma subscript epsilon and B is also part of sigma subscript epsilon. So A and B could also be empty string, right? This means that the first symbol of X is A if A is not empty, and the last symbol of X is also, if the last symbol of X is B, right? So we can write X as A, Y, B for some string Y, right? So we know that A takes the PDA from P to R by pushing T, and B takes the PDA from S to Q by popping T, right? Because that we just said this, right? This also means that Y takes the PDA from R to S, right? So maybe I'll just draw it here. I'm just trying to find some space to draw. So, right, so initially it was empty, and the symbol, upon reading the symbol A, you push a T, and then you read a Y, which eventually gives us the same situation. The same T is still retained. It never becomes empty, right? So always this T is always there. All the intermediate steps, this T is there. And finally, B takes out this T, right? So this means Y could also take the PDA from R to S. So the state here is small p, R, S and Q, right? So this means that Y could also take the PDA from R to S on an empty stack, because it retained the stack, means it can also take it from R an empty stack to S an empty stack. So by induction, we assume that all such strings that take it and Y takes it in k minus 1 steps, because the beginning step is here by reading A and the last step is by reading B. So Y takes it from R to S by retaining the stack in k minus 1 steps. By induction assumption, right? So the assumption was that any string that takes k steps or less is generated by the corresponding APQ. So this means that ARS generates Y, right? And since by already we observed that A takes P from P to R by pushing T, which is encoded here, right? B takes P from popping T from S to Q, which is encoded here, right? This means that because we have these two conditions satisfied, this means that APQ gives ARS B is a rule. APQ gives ARS B is a rule, right? Because these two conditions are satisfied. Because we assume that these movements happened. So we know that APQ gives ARS B, and we have to show that APQ gives X, right? We already have seen that ARS gives Y, right? So now we already have seen that ARS gives Y, so which means AYB is generated. But what is AYB? We already assumed that X was A by B, right? So this means APQ derives X, right? Which is what we wanted to show. So if the stack never became empty, which meant that the symbol pushed in the step 1 is the same as the symbol popped in the last step. Now that allows us to infer that A pushed something and B popped. There are rules where you push something initially and the same thing is popped at the end, which gave us these two conditions, and by induction we could infer that ARS derives Y, and combining all this we get that APQ derives X. The next case, so this was case 1, the stack never becomes empty. The next case was when the stack becomes empty somewhere in the middle. So which means initially you are at state P, then you finally you are at state Q, and let's say it became empty in state R somewhere in the middle. Okay. So suppose this is the entire string is X, right? Suppose the string that took you from P to R was Y, and the string that took you from R to Q was Z, right? X is, so which means X is YZ, right? Now X is derived or X is to process X, it requires k plus 1 steps, right? That's by assumption. Now we know that Y takes the PDA from P to R in less than or equal to k steps, and Z takes the PDA from R to Q in less than or equal to k steps, right? Because both of these movements have to take at least one step, right? Hence, so when the stack empties by the middle, Y is the substring that takes the PDA from P to R, right? Which is what I have said here, in some L number of steps, where L is at most k, and Z takes the PDA from R to S in some k plus 1 minus L steps, again which is less than or equal to k. And we assume that X is YZ, right? Because X is YZ, right? Y and Z together comprise X. By induction, since Y took the PDA from P to R in less than or equal to k steps on an empty stack, it follows that APR is derived from APR derives Y, right? That's the induction assumption. Whenever there is some string that takes it from state P to state R in k steps or less, APR derives that string, right? So since Y takes it from P to R in k steps or less, APR derives Y, and since Z takes it from R to Q in less than or equal to k steps, RQ derives Z. So okay, again there is a typo here. So APQ, the first step is, so we know that APQ derives APR, ARQ is a rule, right? For all triplets PQ and R, that such rule is there. And we know that APR derives Y and ARQ derives Z. So APR, ARQ to derive Y and Z respectively, and that Y and Z together form X. So this gives us that APQ derives X. So even in this case, when when the stack empties in the middle, we are able to see that any string that takes the PDA from P to Q is derived by the variable APQ. And that completes the proof of claim 2.31. Right. So, just to summarize, claim 2.30 and 31. 30 said that if APQ generates a string, then that string can take the PDA from P to Q on an empty stack or by retaining the stack. 2.31 said the converse. If a string X can take the PDA from P to Q on an empty stack, then that string is generated by the variable APQ. So, together we get that APQ generates exactly those set of variables that take this PDA from P to Q on an empty stack, and that was a missing piece for us to show that the grammar that we generated, that we constructed here, is a grammar that is equivalent to the PDA that we began with. Right. So, this completes the proof of the equivalence of the PDA of the grammar constructed with the PDA, and we together with that we are also completing the proof of the fact that any PDA or the fact that a language is PDA, a language is context free if and only if it is recognized by a PDA, right. So, maybe I will just which means PDAs and context free grammars, both of them generate or both of them recognize exactly the same class of languages, which is context free languages. So, maybe I can just state as a result, maybe I am just repeating this, a language is context free if and only if it is recognized by a PDA. So, the class of languages recognized by PDAs are exactly the same as the class of context free languages. So, this completes the proof, even though as I said, even though this proof 2.30 and 2.31 may have seemed long, they are not really that complex. We are just using the basic induction, and we are trying to understand what is happening in the derivation of a string from the grammar and the processing of a string by the PDA, and we see that there is a direct equivalence. And this completes the equivalence of CFGs and PDAs. In the next lecture, we will see ways to show that languages are not context free. So, just like we had pumping lemma for regular languages, we will see pumping lemma for context free languages in the next lecture. So, I think we will stop lecture 24 for now and see you in the next lecture, lecture number 25.